By the end of this lesson, you'll be able to describe what fundamentally creates a magnetic field, describe the magnetic field formed by current flowing through a wire, draw and interpret vectors going in 3 dimensions, and describe magnetic field formed by current flowing through loops of wire. Here we go. If you're a note-taking type person, foundational fact number 1. Moving charged particles create a magnetic field. Moving charged particles create a magnetic field. This is foundational fact number 1. Yeah, I'm not going to check it, but you will need to know it. Mhm.
Oh yeah, we wrote this down last night. I'm so
All right, so we got that down. Hopefully you did. All right, so where do we find a bunch of moving charged particles? In a wire. Come on back here. You're going to be getting up and down a lot. All right, you're looking at the compasses on top of the box. So if you can't see the compasses, it's kind of okay. Once you've seen them, back away so other people kind of like just circulate. Oh, I need a video camera.
No, it's a little high for you though. It is. I understand. Too tall.
Sorry, video spectators. Oh, forgot about you. You guys get like front row seats here. All right. So what we find, we have a wire, and all the compasses are pointing that way, north. Okay, due to the Earth's magnetic field. Okay. Now we're gonna plug this up. I'm gonna throw up the motion sickness here. And we've got wire. Okay. Now what I'm gonna do is I'm gonna plug this up. Now notice. Oh dear. Notice the direction of the compasses. So go ahead and move around.
Oh wow, it's making a shape.
That was actually.
Oh, it's like
That's really nuts.
It's wild.
they're like all.
Okay. Come up and look at the compasses. The pattern they're making. Come on up. I mean, it's the whole point of the demonstration.
Wait a minute.
I know. If you haven't.
Oh, it's a circle. Oh.
Okay. Now, what you're gonna do? This is kind of like the secret handshake of physics. Okay. You know, you've gone this far. I feel like I can induct you into like the physics. Okay. So right hand. Everybody get your right hand out. Okay. Your fingers represent the direction of the magnetic field. Okay. So if we stick our fingers in the direction of the magnetic field, they're going around like this. Okay. And I want to grab the wire.
I can't.
Yes, you can. Keep. There you go. There you go. Okay. Now, Your thumb goes in the direction of current. So the current is in the wire. So in this case, it's going down. Does that make sense? Okay. Now, show me what the direction is going to be if I flip the direction of current. Okay. Ready? 3, 2, 1. Bloop. You verify that with your right hand, and then go sit down.
Wow, that's crazy.
Oh yeah, that's it.
Oh, okay.
I just
This is my like kind of hard. Can't remind me of me.
wait, so the red is which way
Yeah.
it is.
Yep. Okay. All right. So, folks, I don't know if this dawned on you, but we just observed a magnetic field without a magnet. Craziness. I mean, that's kind of cool. Great question. It is. So our compass is a magnet, but what it's doing is responding to the magnetic field that it's in. It's not creating. I mean, it is creating its own, but it's a really small one. So it just responds to the magnetic field because it pivots. So those compasses are magnetic field indicators. Okay. So um, this doesn't just happen in the plane. It happens all along that wire. Okay. It's stronger closer and weaker farther away. Good with that? So see if you can figure this out. Okay, I'll give you one suggestion. Number one, use your pen or pencil as your wire and grab it. Second, second suggestion is embrace your right hand. Like this is going to be awkward and weird, but everybody's doing it. Okay. So like the test is kind of fun. It's like hands on. Okay. It happens. Okay. Correct answer is A. Is everybody good with this? It's going around like this. Okay. Now that's a three-dimensional. Like you have to think three-dimensional. Most people don't like drawing like that. So what we've done is we simplified it using X's and dots. Okay. Circle with a dot. I don't know if this made sense in the video, but coming out of the board at you, this is the arrowhead. Okay. Coming out of the page at you, you need a duck. Like, it's out of the page, out of the board. This is the tail of the feather. Sorry, the tail of the arrow, the feathers, as it goes away from you into the board. Does that make sense? Okay. So on this question, it's the same scenario. You're trying to decode or encode this diagram with X's and dots. It goes in, comes out. Mm-hmm. Tell your neighbor. Correct answer is A. Okay. On this side, your finger is going into the page. On this side, your finger is going out of the page. See that? Okay. Make your pencil or pen the wire. And make sure you're using your right hand. It's called a right hand rule for a reason. Okay. Here's another trick to deciphering or understanding this. Remember our tennis ball on the string, dodgeball? Okay. Pretend, so you're grabbing this, thumb is going to the right. The tennis ball is spinning around like this in the direction your fingers were going. And you're going to let go at point P. Which way is the tennis ball going to fly if you let go at point P? Out of the page. Does that make sense? Okay. So you let go of the tennis ball at that location. Get with a partner. Contribute your right hand. You need two right hands. You don't need a right hand and a left hand. You need two right hands. One person be one wire, the other person be another wire.
So if we release it to stay like the middle.
Here you're going. You good?
I'll let you know twice.
Okay. You go down.
Down?
You go down.
What do you mean? Am I doing it right?
No, yeah. You're the left. Sorry, you're the right wire. I'm the left wire. Okay. So, is the magnetic field going in the same direction or opposite direction at point P? Well, this one's going around like this, but at point P, it's going into the page. That's when you're letting go. This one's going around the opposite way, but at point P, we let go, and it's going to also go into the page. So both of them together contribute to the net magnetic force, the total magnetic force going into the page. You all right with that? Follow-up question. Talk to your neighbor.
We're usually down on the first day.
I bet it gets stronger.
No, it does not. Jason.
Okay, but think about this. Say you have, well, it's compared to like a day. Say you have
The SAT might be smarter than
Okay, what do you say? Okay, when we turn off this, the current on here, that gets rid of that magnetic field. So it gets weaker because they're both going in the same direction, contributing to the total. Take away one of them, and you have a weaker magnetic field.
This is just too quiet. Don't look at me.
Not looking at you.
Just keep going.
Get with it, buddy.
That's the one's pushing this way, and the other one's pushing right. The net force is 2-0. That's what it's like. What's happening?
That's not what it is.
Correct answer. Correct answer is? Correct answer is C. Okay? Because they're equal distance, because they have the equal amount of current, the magnetic fields have the same strength, but they're going in opposite directions. So they cancel each other out. Next question. The arrow's direction of current flowing through the wire.
So if it's facing up, then it's this way. Or if it's facing down, it's this way. And if it's facing this, it's this way.
Could also go this way.
But then it goes, wait, what?
I can make that wire go any direction I want to. Like, it doesn't matter. But you just make you grab this with your thumb in the direction of the current.
Okay.
That's what matters. Okay. Tell your neighbor, tell them why you think so.
Yes, because it weighs.
That one doesn't, but I don't know if like that farther away it is.
Oh, dude, that guy is so awesome. It's like scary. Oh, he's a commando. Right?
Rachel, did you have to do this? Yes. First yes.
All right. Correct answer is? Correct answer is B. Okay. This guy's creating a magnetic field going outward. B. Out of the page. Creating a magnetic field going outward. This guy's creating a magnetic field going at point P inward. into the board. Why is it not 0? Yep, this one's closer. The magnetic field is stronger from this guy because it's closer than this one. So the net is out of the page. Follow-up question. What happens when you kill the current and the right wire? Correct answer is when you get rid of this, the net magnetic field gets stronger because you don't have now this opposing magnetic field. Infinite, but it's super stupid weak.
Okay, so it's obviously increasing.
Yep.
So it's like there, but like we don't know.
Right.
What would be opposing magnetic field that matter because it was going?
No, it was going. So so this guy's creating a magnetic field going into the board. Right, because one's going out with 10, the other one's going in with like 4. So the total is 6.
Oh, but it's okay.
Does that make sense? And then if you take the 4 away, it's 10. Yep. All right. I'm going to take my wire and I'm going to put it in a loop. My suggestion for evaluating this is look at each side. Left side, top side, right side, bottom side. Evaluate them separately and figure out the direction of the magnetic field at point P. Left side, top side, right side, bottom side. Correct answer is B, Buster Brown. Okay, so here, find that's going from the left side at point P in, the top in, the right in, bottom in. You got all 4 sides contributing to this magnetic field going inward. Good with that? Tell your neighbor.
But I don't know if he would tell me.
I'm gonna go with physics helps me so much on that SAT. Like, there's some stuff like ask for like velocity.
Bro.
Wait until.
There was one about velocity. I don't know if I did it right though, because it was from my first semester.
It was a kinematic equation.
It was like, wait, what did you do?
Wait.
I did.
If you ever take the ASVAB, it's loaded with physics.
That's probably why my
But the better you do, the better. Like if you go in the armed services, like
I think I'll do better on the ACT than I do on the SAT.
all right. Correct answer is A. Why? Because you've got magnetic fields from each of the sides contributing inward.
You're still English on the ACT? Then why would I even take it?
All right. So, is that, folks? Here we go. Here we go. We'll talk about SAT after the video is over, and I'll clear you straight. So, folks, here's the deal. By putting a wire in a loop, we just increased the strength of the magnetic field by close to 4 times the strength. Okay, that's crazy. Okay, so rarely do we ever like make a square loop. That's just for your ease of convenience of like which side should I use. Usually it's in a circle, but the same effect. The magnetic field is going in the same direction at all parts. A was, yeah, the loop. Okay, so when we add all these together, you get this type of pattern of the magnetic field. Okay, the magnetic field is strong in the middle. Okay, now to evaluate this three-dimensional picture, here's what we do. Ready for this one? It's going to take, you should stop playing chess and you should focus on me right now. So you're going to look at the part of the ring, at part of the loop that's closest to me, closest to you. Is this part closest or this part closest? A or B? A. You got to look at it three-dimensionally. You're going to grab the closest, you're going to pretend your pencil or pen is this closest part. You're going to grab that with your thumb in the direction of current. Okay? Because this is closer, what I care about here's what the part that's in here, this middle part, this is the part that I care about. I want to know the direction of the magnetic field in the loop, in the middle, in the interior of the loop. So I'm putting my pencil here behind, I'm putting my fingers behind this because this is inside the loop. Does that make sense? My thumb's going to the right. I'm looking at my point P is here inside the loop. I'm going to let my tennis ball go at point P. Which way is it going to fly? Up. That is the direction of the magnetic field inside the loop of wire. You all right with that? Okay, so here, just kind of showing you like spinning this around, looking at the magnetic field, but it's also three-dimensional, so it's really strong. Okay, good with that? All right, so here is a three-dimensional ring. This is the side view. We're looking, this is the closest part of that ring. Talk to your neighbor.
No. Wait. It's just so cool. It's just definitely. I was like, I felt so confident after you said
No, you're which way was based on the arrows. That's super right. Gotcha. Okay. It's curving. Oh yeah, it's going.
What do you say?
Buster Brown. B for Brown. No, Buster
Agreed. Buster Brown.
Yeah.
Okay.
Good job, B-Rob.
So your fingers are going down. Let's just start with that. Okay. It's either going to the right or to the left. Those are your options. Okay. Okay. Your pencil represents the part of the ring that's closest to you. Okay. And you're going to try to grab that. You cannot grab your pen like this, but you can do it like this. So your thumb is going to the left. This represents the magnetic field inside the loop of wire. Okay. Come on over here for another demonstration.
No thanks.
Okay. What I have here is some loops of wire. It's actually one wire just wrapped a whole lot of times. Yep. One wire. Okay. Now, if I take my compass, I stick it in there. Facing north. Okay. Are we good with that? Now, when I turn this on, when I turn this, okay, all of a sudden, ready? Ready? Okay. You've got a magnetic field going this way through the loops of wire. So, show me what's the direction of the current going through this part of the loop here. If you got magnetic field going this way, magnetic field's going this way in the direction of the red arrow is pointing. This way. Magnetic field's going this way. So what part of your hand represents magnetic field? Fingers. So stick your fingers which way? And you'll be going in the direction of the magnetic field. Now, I can't grab the wire like this, but I can grab it like this. Thumb shows me the direction the current's going through this wire. So the current's going this way. How we doing?
I don't know how he.
Grab the part of the loop that's closest to you.
why couldn't you just grab the bottom of the ring? That's so close.
Yeah, I know.
You could grab the bottom of it like this and then you're pointing that way.
No, you see it go that way.
Oh.
So why would that be?
I mean, I'm not saying you can, but just this is the easiest way to do it. Okay, good with that? Now, we're going to do a little bit of a iron filing sprinkle. Okay.
Mr. Smiley, what happened if you ate those?
Get some iron in you.
Okay. Yeah, healthy, right?
You'd poop most of it out.
Would it like shred up my throat if I swallowed it?
Yeah, it wouldn't feel good. Kind of like swallowing glass.
Oh.
Like it'd pass through, but do some damage. So here we see boogers. We see no pattern. Current's not on. Okay, but when I turn on the current, you see the pattern. Okay, good with that? Yeah, birch tree, aspen tree. Now, if I take something that is made of ferromagnetic material, iron, nickel, or cobalt, this is steel, has iron in it, and I place it in here, this automatically becomes magnetic. Okay? Nor can you turn that off the box. When I turn it off, it's not as magnetic. Go ahead and turn it back on. I just created a what? Oh, I'm looking for a certain word.
Oh, starts with an S.
The last slide on the pre-quiz. Nope. Nope. Electromagnet. Okay, it's electromagnet. It's a magnet that you can turn on and off. Okay, now notice this is slightly magnetized. Okay, because it caused some of the domains to actually switch because it was in this magnetic field. Okay, now if I drop this, okay, now it's slightly magnetized, but definitely weaker. Okay, I caused the domains to become scattered.
Is that why, like, when I first got a drill bit, it was like magnetized, but since I've dropped it for like 12 years, it's not magnetized anymore?
That's the reason. Now,
How do I remagnetize it?
oh, JP, you like set me up. Okay, so this guy right here, ready? Where do magnets come from? Okay, so these are two coils of wire wrapped around toilet paper rolls. Okay, I'm going to stick one in one side and one in the other. And I put a piece of iron on top to channel the magnetic field. Right there, I just allowed current to go through those coils of wire in the box. And I just magnetized these magnets.
That's wild. If you held the button, would it make it like super strong?
Mm-mm.
What if you put your fingers?
It doesn't. It's fine. Now, so here, north and south, they attract, but if I go south and south, they repel. Now, watch this. I'm going to load these in incorrectly.
It's gonna blow up.
I wish you
Ready? South and south.
No.
Okay.
Opposites can attract. I've lost.
Okay.
Too much physics.
That's what that means. Okay. So I just made the domains go in the switch directions going the other way. Okay. South and north, repel. Okay. Now I'm going to remagnetize it correctly so not to mess with people.
You should mess with people.
I know that's being a bad teacher.
That's being
That's not. That's horrible education. Like here, kids. Like I knew a teacher that was like, hey, I'm going to teach my kids that red is blue. It's called blue, and blue is called red, just to see what happens. And like that is such a jerk move.
It'd be funny though.
It
probably was funny.
Just
So-
watching the kindergarten.
Okay. So and we put it back. Okay. Good with that? Okay. Have a seat.
every day. This is my least favorite email. I really don't like it. It's making my mind mad. Like whoever made magnets, I just think I'll fall off the face of the earth. And then be confused on why they do because they didn't magnetize it. They didn't magnetize it.
All right. So I want you to use what you know about circuits. So this is the positive terminal. This is the negative terminal. This compass is going to be placed on the interior part of this loop, just like what we just did. Okay? This is connected to the positive. This one's connected to the negative. Which way is this compass going to point when it's on the inside of that loop?
So it's looping like this.
Mm-hmm.
Wait, is the compass like what it's going in the circle?
The current's going in a circle. Well,
Wait, which one's your thumb and which one's
sorry. Thumb is current. Fingers are magnetic field.
like how do you know which direction to point your hand?
So you're going to look at the part of the coil that's closest to you and try to grab that part with the thumb going in the direction of current.
Like how do you know which is
All these are closest. Behind here, that's far away. Okay. Current goes out of positive into negative. So current is going to the right. So I'm going to stick my thumb to the right. Okay. I'm going to try to grab this part of the wire because it's the closest part of the loop. can't grab it like that. Wait a minute. Sorry. I can't grab it like that. I have to grab it like this. So my fingers behind this are going up. Current's going this way. I'm going to make this my pencil. My pencil, my wire. I'm going to stick my thumb in the direction of current. I'm going to grab it. Behind here is in the middle of that coil. So magnetic field is going up. C. C. Because you're going to let go at point P, which is inside. Okay, you're looking on the inside. Okay, if I'm looking at this wire, the point that I'm trying to find is inside the loop. Is that going to be out here, A, or behind the plane of this board? Sorry. Here, okay. This represents this part of the wire. Inside the coil is going to be out here, A, B, C, or D. Inside, where is inside the loop? A, B, C, or D? D is inside the loop. This is the top part of the loop. We're on the inside. Right here is where I care about. And this is where I'm sticking my compass. I'm grabbing this with current going this way on the inside of the loop where D is going up. Okay. So if we wrap a whole bunch of these loops together, we get a solenoid. Get a really strong magnetic field in the middle. Okay. Has a lot of applications. Okay. So this is looking at a plane. This is kind of looking at the iron filings, but it's also three-dimensionally, JP.
So if I consume iron through food,
yeah.
Is it possible for me to get magnetized?
No. No, the whole like Magneto, like X-Men, yes, no, is that too old?
I know X-Men. Magneto's pretty dope.
Like when they inject that guy with iron and it pulls the iron out of the blood. Not like that.
But what if he's But what about Iron Man? That's possible.
Sure, because that's his costume. Okay, so everybody good with that? All right. Take in what you know about magnets, and then this lesson. Okay. You gotta watch. We're talking about the inside or the outside of the magnet. Magnetic field lines go out of north into south on the exterior part outside the magnet. Inside it goes from south to north. This is the inside. This is the outside. Okay? Correct answer is A.
Those U-shaped magnets, one's south and one's north, but they're both pointing the same way.
What is they? What is
like north and south? They're both like this.
Yes.
They're both going the same direction.
So a horseshoe magnet. We'll talk about this more tomorrow, but it goes out of north into south. That's what your iron filings lab showed you.
So what does it do on the inside of the magnet?
They form loops. Okay. 2 more questions for you. This one and next one. My suggestion would be to look at this part of the loop because it's closest to you. Tell your neighbor. Go, go on the right hand side. No, because I am looking at the part that's closest to me. On the left side, that coil is far away. This side, the coil is close. This one's here. The other one's deeper. This one's closer than that one there. It's going around like this. So this is closer than this. I'm looking at the closer part. You know? Okay. So, correct answer is C, caramel cakes. Okay. So, current's going up. Looking at this part, sticking my thumb up, and I'm grabbing this behind this wire inside the loop. My fingers are going to the left. Here's my wire. I'm going behind it. I'm looking at the magnetic field. You can chew on that one. Got a pre-quiz tomorrow. Yeah. Correct answer is A.